Hello everyone, I am Anandavelli. Welcome to this new video from Guidance Education channel. We are continuing Class 11 Chemistry, Chapter 4 Chemical Bonding and Molecular Structure. Under that, in this video, we are going to do polarity of bonds. What is the meaning of polarity? Polarity means charge separation. You know that when two charges are separated by a short distance, we call that a dipole. A dipole is best known by a quantity dipole moment, that is magnitude of one charge multiplied by distance between the two charges. Let us take it as 2a. That quantity is called dipole moment. It gives us an idea of polarity. That is how much the charge separation is. Unit of dipole moment is dB, represented by the letter D. 1 dB is equal to 3.33564 into 10 raised to minus 30 coulomb meter. Dipole moment is magnitude of charge into distance. For magnitude of charge, the unit is coulomb, and for the distance, the unit is meter. So, dB is given in coulomb meter. The symbol for dipole moment is mu. We have familiarized ourselves with two types of bonds. Ionic bond, which is otherwise called electrovalent bond. Another one is covalent bond. Ionic bond or electrovalent bond is formed by transfer of electron from one element to the other, and normally bonds between a metal and a non-metal. Let us mark this metal by the letter M and the non-metal by NM. Bond between metal and non-metal. Say for example sodium chloride. That bond is electrovalent bond. Sodium gives away one electron to chlorine. By losing one electron, sodium gains octet structure in the valence shell. Similarly, chlorine also gets octet structure in the valence shell by gaining one electron. Sodium atom becomes sodium ion with a positive charge, and chlorine atom becomes chloride ion with a negative charge. An electrostatic force of attraction develops between these two ions, and that is ionic bond. What is covalent bond? Covalent bond is formed by sharing electrons. How many electrons are shared will depend upon how many electrons are needed to complete the octet. Okay, now it has been observed that ionic bonds have partial covalent character. Similarly, covalent bond has partial ionic character. What does it mean? In the case of covalent bond, if it is 100% covalent bond, that is 100% sharing of electrons, the shared pair of electrons will be in the center between the two nuclei. That happens only in molecules like hydrogen, chlorine, fluorine, etc. That is in homonuclear molecules. But in diatomic or polyatomic heteronuclear molecules, covalent bonds will not be 100% covalent. They will have partial ionic character. That means they will show partial charge separation. That is polarity. So, in the case of nitrogen, hydrogen, oxygen, chlorine, fluorine, etc., that is homonuclear diatomic molecules, there is no charge separation and they are called non-polar molecules. But in heteronuclear, covalent molecules like water, beryllium fluoride, boron trifluoride, nitrogen fluoride, ammonia, etc. There is polarity. We will try to understand the net polarity of these molecules one by one. First, we will take up water. We have already learned that in the case of water molecule, the two OH bonds are at an angle 104 degrees. As oxygen is more electronegative than hydrogen, the shared pair of electrons in the bond will be pulled towards oxygen atom. So the hydrogen atom develops a delta positive charge and oxygen atom develops a delta negative charge. Therefore, the dipole moment will be directed towards the oxygen atom. Dipole moment is a vector quantity. The dipole moment is represented by a cross arrow. The arrowhead directs towards the delta negative charge and the cross tail the delta positive charge. Please note it in the diagram. This is true for both the bonds. Here you have two vectors directed to a single point. The net dipole moment will be the vector sum of these two dipole moments. Will be in this direction. The net dipole moment of water molecule has been calculated to be equal to 6.17 into 10 raised to minus 30 coulomb meter, equal to 1.85 dB, which is approximately equal to 2 dB. I have already given the magnitude of 1 dB. So divide this quantity with that quantity. You will get it as 1.85, which I have approximated to 2 dB. Now let us consider beryllium fluoride. Beryllium is the central atom and the two fluorine atoms are attached to it. Fluorine is more electronegative than beryllium, so the dipole moments of the two bonds is directed away from beryllium atom. So you have two equal dipole moments in opposite direction. The net dipole moment of the two equal but opposite dipole moments becomes equal to 0. So in the case of beryllium fluoride, the net dipole moment is 0. This is a favorite topic for examiners. Questions are asked from this topic. So this is second one. Now the third one, we have done these two. Boron trifluoride. Boron is the central atom with 3 fluorine atoms held at an angle 120 degrees each. Fluorine is more electronegative than boron. Therefore, all the 3 dipole moments are directed towards the fluorine atom. Their magnitudes are the same. For convenience of explanation, we will number these boron-fluorine bonds as 1, 2 and 3. It has been found that the resultant of any two of these dipole moments will be equal but opposite to the dipole moment of the other bond. Say for example, the resultant dipole moment for bond number 1 and 2 will be equal but opposite to the dipole moment of the third bond, or the resultant dipole moment for bond number 2 and 3 will be equal but opposite to the dipole moment of bond number 1. So also the resultant dipole moment for bond 3 and 1 will be equal but opposite to the dipole moment for bond number 2. Therefore, net dipole moment in this case also is 0. Now we will take up that for nitrogen fluoride and ammonia. Both these molecules, that is 4 and 5, have 4 atoms. They are tetraatomic. and both of them have pyramidal shape. But it has been observed that the net dipole moment of nitrogen fluoride is much less than that of ammonia. This is one favorite question for examiners. You may be asked to explain why the net dipole moment of ammonia is less than that of nitrogen fluoride. Let us see the answer. In both the cases, nitrogen bears one lone pair. You should always remember that. You can give the explanation for this question only if you remember this point. Now let us represent the two molecules. For ammonia, this is the nitrogen atom and this is the orbital of the lone pair. And there are 3 hydrogen atoms attached to this nitrogen. You know, the electronegativity of nitrogen is greater than that of hydrogen. Therefore, for all the 3 bonds, the dipole moment direction will be towards the nitrogen atom. So, the resultant dipole of these 3 dipoles will be in this direction. That is, in the upward direction from the nitrogen atom. The orbital dipole moment due to the lone pair also will be in the same direction, directed upward. The net dipole moment of ammonia molecule will be the vector sum of these 2 dipole moments, which is equal to 4.90 into 10 raised to minus 30 coulomb meter. Now consider nitrogen fluoride. Nitrogen is the central atom. There is the lone pair, that is the orbital of the lone pair, and 3 fluorine atoms attached to this nitrogen. But in this case, fluorine atom is more electronegative than nitrogen. Therefore, the dipole moments of all the 3 bonds will be directed away from the nitrogen atom. That is, in the direction opposite to what you saw in the case of nitrogen-hydrogen bonding in ammonia. And the net dipole moment will be directed downward, that is away from nitrogen. Whereas the orbital dipole moment will be directed upwards. The orbital dipole moment will be much less than the resultant dipole of the 3 nitrogen fluorine bonds. So the net dipole moment for nitrogen fluoride will be the sum of, that is the vector sum of these 2 dipole moments, and that is equal to 0.80 into 10 raised to minus 30 coulomb meter. This is very less. What is the reason for this reduction? This is because the 2 dipoles, that is the orbital dipole moment and the resultant dipole moment for nitrogen fluoride bonds, are in opposite direction. In the case of ammonia, the net dipole moment is more. This is because the resultant dipole moment for the 3 nitrogen-hydrogen bonds and the orbital dipole moment are all in the same direction. I hope I have cleared your doubts. Hope this video was of great use to you. If you think it is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do support me by subscribing. We will meet in the next video with the next important topic. Till then, bye. Take care. We shall discuss Fajans rule in the next video.